Okay, let's go ahead and get started. So it's a pleasure to announce Raissa D'Souza, who's going to be talking about statistical physics, computer simulation, and probability.
Hi, thanks for inviting me. It's a really fun meeting so far. This talk is going to be quite different than Dave's. That was a beautiful talk, hard to follow up. But I'm going to talk to you a little bit about sort of more of an overview. So I only have half an hour. Instead of getting into anything really specific, I'm going to talk sort of at a high level and show you a couple models that really illustrate this intersection between statistical physics, computer simulations, and probability theory, which have this rich interplay. And my own background really comes from the statistical physics world, so that's been all of my training. I've done a lot of work in computer science as well, so naturally now I'm faculty in a mechanical engineering department. So this is new. This was, as of last October, I joined the faculty at UC Davis, and I'm also in a center called the Center for Computational Science and Engineering. So what I'm going to talk to you today a little bit is about some models. Okay, and models can be really useful on many levels. They really give us sort of a framework for thinking about complicated processes. So we might try and simplify the essence and sort of get a qualitative understanding of phenomena. So models are really useful for that and sort of guiding our intuition and giving us some structured way to think about a problem. I work a lot with mathematicians, so we're trying to understand phenomena and get some intuition about what we should be proving. And one of the models that I'm going to talk to you about was exactly that. A lot of people have worked hard to try and prove a certain phenomena, and then we found that phenomena actually wasn't there, so it's not a big surprise that they couldn't prove it. And lately I've been trying to work a little bit with engineers, like with network engineers and with people building sensor networks, trying to do some theoretical work before they go and do any implementation. So we've been doing a lot of modeling in that aspect as well. And really the thing that unifies all the work that I've done personally is this concept of self-organization, which is when the internal degrees of freedom of a system gain some internal organization without any external control. So I've looked a lot at things like growth of molecular aggregates. This is a model I'm going to talk to you about today, which is about jamming and pattern formation. Okay. I really like to point at the slide, so I have to use the microphone. And I've done a lot of work on network growth as well as looking at self-organized networks. And really, I want to talk to you about this intersection between these fields. And I want to think about probability and statistical physics, which are in the two corners. And I really want to think about computer science as a discipline distinct from computer simulation. They have overlap, but they're very different things. And this intersection is really rich and has a lot of interesting shared phenomena and shared techniques. And when we go out from that intersection more along the computer science line, we're unified by network models. So we think a lot about Boolean networks, circuit networks, Bayesian networks, random networks. And when we go out towards the statistical physics axis of things, we think about lattice models like the Ising model, the Potts model, diffusion limited aggregation. And there are common phenomena that unify all these things, basically concepts like phase transitions and percolation. And there's also tools like computational complexity theory, which unify their techniques that we use to study all these models. So even though the disciplines might be disparate, there's a rich union between them. And a lot of this work, when you look at that intersection and head out towards the computer science end of thing, you find networks. And there's so many concepts that overlap between the two fields. So there's a lot in statistical physics, we're always trying to deal with locality. So we want to just have to understand what's going on locally in a system to predict large-scale behavior. We want a lot of things to be self-organized, and in a network context, we want to have scalable growth. So we want networks to grow indefinitely large without gaining additional control, overhead control. We look a lot at scaling behaviors, and we look at how fluctuations affect the physical models that we're dealing with. And in networks, we're very interested in how fluctuations relate to routing and load balancing. So there's a whole rich world that involves the intersection and in this network context. But today I really want to focus on lattices. So I'm going to think more about traditional statistical physics models, which are really rooted in lattice models. So much of the modern phenomena that we study in statistical physics is based on some really fundamental lattice models. So most modern statistical physics, the study is really involving critical phenomena and phase transitions. And the prototype of a model that shows a phase transition is the Ising model. And extending that is the Potts model. And we're really interested in things like percolation on lattices as well, and different kinds of lattices. And there's also critical kinetic phenomena that we study a lot, like diffusion limited aggregation. And a model I'm going to talk to you about today, the Beham-Middleton-Levine model. And these models are really highly influential. They shape our thought processes and give us grounding to move forward. So they're really the cornerstone of modern statistical physics, is thinking about these models. And the interesting thing is that these same models are studied in probability theory. And so and a lot of them are accessible only through computer simulation. So these three fields of probability, statistical physics, and computer simulation are intimately related by the study of these shared models. And it's very interesting to have dialogues with people from the disparate communities, because you find that you can make a lot of progress on your own work by realizing where your faults were. So it's an area that is becoming much more active, and there's been a few workshops at MSRI in the last couple of years. I know I've seen several people in the audience at the last year's semester that was on probability, statistical physics, and algorithms. So there's a lot of amazing phenomena going on at that intersection. And what happens with these models is that they can get very complicated, especially the nonlinear ones. So I'm interested in dynamical models of nonlinear phenomena. So they can get incredibly complicated to try and understand analytically. So a lot of what we have to do is proof through computer simulation, or explore the phenomena through computer simulation. So I think Dave had a nice example when he was showing that cock tool that helps you prove mathematical theorems. So we're seeing math sort of take on this new branch of experimental mathematics. And one of the things that's really we have to keep in mind is that there's a lot of caveats that we have to keep in mind when we want to try and extrapolate between these three fields. And one of the crazy things is that sometimes we get results from simulations that contradict theory. So the classic example of this that came out recently is Bootstrap percolation. So people were looking at this model in a computer implementation, and they were finding that the critical density for percolation was a particular value. And it had been converging and being over and over again iterated, and it was getting to a crisper and sharper value. And then people actually finally managed to prove the percolation threshold in the infinite lattice, and it had absolutely nothing to do with the results from simulation. So they were orders of magnitude separated. So what's going on? So that took a couple of years to figure out what's going on, and really one of the caveats to keep in mind is what the length and timescales of interest are and what your tools allow you access to. So in the world of simulations, we're dealing with really small length and timescales, so it's whatever is accessible in my computer. Clearly, even if this is a supercomputer, it's a small length and small timescale. If you look at mathematics, almost all the results are in the asymptotic limit, where we're thinking about infinite time, infinite size systems. And physics, which we're really interested in modeling, kind of lies between these two worlds. So it's not in the finite size of computers, and it's certainly not in the asymptotic realm either. So we really have to keep in mind, what are we trying to explain? So what tools do we need for that particular phenomena? And keep these caveats in mind. There's another big caveat when we think about doing computer simulation and probabilistic models as well, and that is that a lot of them are discrete time processes, and they rely on synchronous time updating. So you have a game like checkers, where you alternate players, and it's a deterministic process. And in a lot of the models that I study, we have synchronous time, and all the dynamics occur in lockstep. And this makes the models nice, but it sometimes adds artifacts to the results, the phenomena that we see in those models. So this is another big caveat that we have to keep in mind is, when is this a reasonable assumption? So there are some times that things should be synchronous, but it's not true in general, and we have to keep in mind that most of our models have this quantity. And then there's also things like lattice effects and boundary constraints that we have to keep in mind. So I was working on a model, and it's this Beham-Middleton-Levine traffic model. And I think it's a really nice illustration of some of these points. And so I'm going to step through this model and then kind of bring in a few other models from probability and statistical physics as we go through this. And at the end, sort of give a little bit of an overview of the lessons that we learned from these different models. So this is a really simple model. It's a really beautiful model. It's a model of cars moving on a lattice. So there's two species of cars. There's red cars and blue cars. And the red cars all try to move to the right, and the blue cars try to move north, and they alternate time steps. So on even time steps, all the red cars try and advance one site, and on odd time steps, all the blue cars try and advance one site. And they live on a torus. So if you come up here, you come back on here, or come up the top, et cetera. So it's on a torus. It's a 2D torus. And what we're going to do is sprinkle the cars down at random and let the dynamics run. So if we just had a 1D system, like I've drawn here, there's a line of red cars moving to the right. They end up getting spaced every other one because you move as long as the site you wish to occupy is empty. So the 1D problem's pretty trivial. As long as the density is less than 1/2, all the cars manage to space out every other car, and they all move with unit velocity at each time step. And as the density gets greater than 1/2, you'll start getting some cars that are jammed together and stuck, and that jam will sort of propagate backwards. So in 1D, it's a very simple process. And what we're interested in is the 2D model, where we have the red cars and the blue cars. And this was the standard understanding of the model since it was introduced in 1992. So the understanding was that at low density, so I'm going to point this out to you. So at low density, the cars manage to self-organize onto non-interacting sublattices. So you get big clumps of red particles that all move in lockstep, so they're spaced out every other car, and big clumps of blue particles that likewise move. So you end up with these stripes that organize through the dynamics, and it's such that all the cars can now move freely. So at low density, the asymptotic state settles down to this kind of situation where all the cars move at all time steps. And then when you start at high density, you end up with one big global jam. So again, this is on a torus, so it's a big jam. Okay, so this was the standard understanding, and the thought was that this was a crisp threshold from free flow to jam, so that it showed a first-order phase transition. So this is what people have been trying to prove for a long time, is the existence of this phase transition and the critical value of rho for the phase transition. So almost all the progress that has happened has been numerical. It's really funny. So the only things that we can prove are that if the limit of the density goes to 0, there's no jam. And then the limit that the density goes to 1, everything jams. So that, but last year, during that MSRI semester, Ander Holroyd and James Martin and, do you remember who the third person is? Omer Angel, thank you. They extended this proof in a beautiful way using some ideas from supercritical percolation theory, and they showed that you can now show that things jam for densities close to 1 but less than 1. So they extended this proof, but it's still far off in this very high dense regime. So this is what people have been trying to prove for a long time. So I started out studying this model a couple of years ago, and I wanted to visualize what was going on. And I do a lot of computer simulation, so some probabilists came to me and said, can you help me visualize this? So I did, and I started finding the step in the center. So instead of finding these two distinct behaviors, I started finding this sort of intermediate-like structures. And they would last for a long time, so I would leave this running for a week, and it would still be there. So I tried to quantify this, so I ran some numerical experiments. And now these are results for different size lattices. So I'm looking at a square lattice up until now, so it's a torus where the number of columns and rows are the same. And the order is 64 by 64, 128 by 128, 256 by 256, and 512 squared. Okay, and on those small lattices of 64 squared, I get this phenomena that looks like a first-order phase transition. So plotted on the vertical axis is the average velocity of all the cars, and this is versus density. So for those small systems up here, it really looks like a first-order phase transition. Everybody moves with velocity 1. They organize into those stripes. And then at a certain density, right around 36%, they all get jammed. But as you start going to bigger and bigger systems, you see that these sort of intermediate states emerge. And there's not a broad range of intermediate states. They're all quantized right around the value of 2/3. And as I got to bigger and bigger systems, it became more crisply quantized. And also that window of phase coexistence broadened. So I was trying to figure out what's going on here because it really doesn't seem to fit the standard model. So this is what an intermediate configuration looks like on a square lattice. And I don't know if you can see it, but there's like little chains floating around inside the mix. So it's not a perfectly ordered system. There's all these microscopic fluctuations and these random chains that move throughout the system. So I was trying to figure out how to make progress on this, and grabbed my attention was the honeycomb dimer model. So this was done by Kenyon and Wilson, and I happened to be working with David Wilson in the same place at that time. So I was talking with David, and he was telling me about some of the pathologies of the honeycomb dimer model. And this is a model for looking at percolation on a honeycomb lattice. And they found that at the critical point of this phase transition on the honeycomb lattice for percolation, that there was a lot of sensitivity to the boundary conditions, so to the shape of the lattice, whether it was a torus or whether the torus was even, so there was the same number of rows and columns or not. So he wanted me to think about my model, not on a lattice where I had L by L sites, but on a lattice where I had L by L prime sites. So really simple tweak. And he said, why don't you think about a different shape of the domain? And I did that, and instead of getting those disordered chains, suddenly everything became very crisp. So this is what a typical intermediate configuration looked like. And in order to sort of try and make the x-coordinate and the y-coordinates of the lattice, so the length and the height, as different from each other as I could, I chose 2 successive Fibonacci numbers. So this is on a Fibonacci lattice of L by L prime. I would do this repeatedly, and I kept finding these perfectly ordered geometric structures. So let me tell you what's going on here. These thick bands are fully jammed particles, and then the thinner bands are things that are spaced every third. So the regions that are less dense here have density 1/3, and these regions have density 1, and they're like a jam interface. And it sort of propagates down through the space. Actually, I'm going to show you 2 things. First, we're going to take a close-up. So this is a close-up of a region just past a jam, and it has this amazing high level of self-organized behavior. So if you can see that region that's just past the jam, okay, let's do this. So they're alternating stripes. So there's a stripe of blue, red, empty, blue, red, empty, blue, red, empty. So the density of this lattice is 2/3, and this is provably the densest packing that you can achieve where all particles move with velocity 1. So what's going to happen is, at the next time step, these blue particles are all going to move north and move into the empty space, leaving an empty row behind them, so that the next time step, the red particles can move to the right and occupy that time step. So this is the dynamics. All these particles in here get to move with unit velocity 1. The particles here are jammed, and then they end up having density 1/3 here because they're leaving the jam in this well-defined order. So there's a lot of regularity to this structure. I have a little Java simulation that will show this, more or less. I also, just as an aside, since I like to do a lot of computational work, I just switched over to using Apple computers. And it's wonderful and it's great, except it runs Java incredibly slowly. So this is really painful. So I was really sad. I hope the new Intel processor is going to help. Random aside. But this is not going to be totally clear. But what's going on is here's the jam interface. So here's the blue particles, here's the red particles, and the jam sort of moves with unit velocity down the space. So I don't think that this is incredibly clear, but I have a lot of great pictures on my website if anybody's interested. But let's turn that off for now. Okay, so let's go back to the pictures. So these are what the jams look like. So they self-organize onto these kinds of structures. They organize onto the densest packing that you can provably show supports velocity 1, which would never happen in a random configuration. And they have these really well-defined orders. So knowing this a posteriori, we were able to formulate some theory about what's going on here. So there's some interactions here between the local dynamics. So there's this protocol for how the red particles and the blue particles move. So there's this local dynamics that's going on to organize the particles locally. And then they have this global constraint that comes from the lattice itself. And mainly the constraint is that the number of times that the blue band wraps around the lattice has to be an integer because it lives on a torus. So the head and the tail have to intersect. So you have an integer winding number for the blue bands and an integer winding number for the red bands. So knowing these things, that we have integer numbers of winding bands and that all the particles are conserved, we were able to come up with some small-scale conservation laws that told us how the particles were going to move. And then we added in the global constraints. So the first two lines there come from the fact that the particles are conserved. So we know that as we count across rows, we get a certain number of particles. And the second constraints come from the fact that they live on a finite lattice. So we looked at the slopes of regions that were jammed and the slopes of regions that were free-flowing and found some way to make sure that as we added these regions together, they added up to the number of sites wide or the number of sites high. So with this, we were able to come up with an equation that had some constraints between the winding numbers and the size of our lattice. So L by L prime is the size of our lattice, which is that first term here. And then that's the winding number for the blue bands, and that's the winding number for the red bands. And S is the slope of the jammed region. So we were able to come up with this equation that gave us some consistency amongst all these variables. And then we were looking at what types of lattices would support these configurations. And we looked at square lattices, and then we also looked at these Fibonacci lattices, which are these guys here, where the ratio is the golden mean. And we know that the slopes, because we observed them empirically, they were all very close to 1. So there were two ways that we could get integer winding numbers and slopes close to 1. So for these Fibonacci lattices, from these constraints, we predicted that we should see two different kinds of configurations with winding with 1 red band and 3 blues, or 1 red band and 2 blues. And then when we actually ran the simulations, this is also what we found. We found that we got these two different configurations, and you can see that there's now the red points are from our experiments, and the dashed blue lines covering the red points are the results from this little a posteriori self-consistency constraint that we came up with. So we see the predicted number of winding bands, and we got that our equations that sort of came from these microscopic constraints interacting with the global constraints match well what we see experimentally. So there's a couple ways to go from here. First of all, why is it this is a model that was introduced in 1992, and it's been studied extensively both in the probability community, the statistical physics community, and the engineering community. So people have used this as a model of actual car traffic in cities. So this is clearly a pretty big problem to model congestion in cars. So people have been studying this model extensively, and since it was introduced in '92, there have been about 250 citations in the literature claiming the existence of this first-order phase transition. So it's like a prototypical model that shows self-organization in phase transitions. So there's a couple questions to ask now. Well, first of all, how come nobody saw this before when it's a model that's been cited hundreds of times and studied extensively? So that's a really good question. Part of my feeling on that, I'm going to just skip over a little bit. So part of my feeling in that is that there's a lot of ingrained traditions that come from doing statistical physics and from doing probability, that you sort of look in your own space and you don't sort of question some of the basics. And one of the basic things that we normally think about in physics is locality. So we normally think that things interact on a local scale, and once you get to a big enough scale, you've washed out any influence that you had from the underlying geometry. So if you're on a lattice, by the time you get to the full size of the lattice, you should have no more effects left. So people don't really try to look at different lattice aspect ratios. And it was really interacting with probability theorists that made us start thinking in those regions. I think the other thing that helps is visualization. So we've got great visualization tools now that didn't exist in '92. But I think that the thing that really prevented their discovery more was biases. So there are several papers that were sort of suggesting that there were some sensitivity to boundary conditions in this model. So of that 250 papers, a couple of them had suggested that there was sensitivity to boundary conditions. But they actually never investigated it further. They just dismissed it as an uninteresting phenomena. Or people also tended to discard realizations that didn't match their beliefs. So when they ran realizations, they expected things to either converge to one of those two states, free-flowing or fully jammed. So if something ended up in the intermediate regime, oftentimes it got discarded because it was just dismissed as something that hadn't yet converged. So what was really good for us, which I forgot to mention, is that once we went to these lattices where we have such precise order, we saw that this order was really persistent. So we ended up, like you'd see one small fluctuation and it would persist for days. So we ended up taking a snapshot and comparing all subsequent microscopic configurations to a snapshot in time. And we found that these things are exactly microscopically periodic. And they have really short periods, too. So this is like 5,000 particles, and the recurrence time is around 5,000 time steps. So these things converge relatively quickly to a steady state that has a very small recurrence time. So it's absolutely not that these intermediate states should be discarded because they hadn't yet converged to one of the two standard states we expected, because they've converged and they're in their limit cycle, so they're never going to get perturbed from that. So that was sort of an interesting lesson about how to do some of this science. And then one of the things that I started playing around with was trying to think of the role of synchrony. So what if now the red cars and the blue cars don't move in lockstep every other time step, but we're just going to flip a coin. So at the red phase, all the red cars flip a coin, and if they get heads, they move forward. If they get tails, they just stop. So now after a number of t time steps, everybody has tried to move a Poisson number of times. So it's a Poisson distributed variable, how many times a car has moved. So we'd call this the Poisson updating model. And what's really interesting is once you get rid of synchrony, we lose a lot of the patterns that had been there. So we lose a huge amount of that self-organization. So this is what things look like. So we no longer see that self-organized configuration of all cars having velocity 1. So that's just never seen anymore. Instead, we see sort of a smooth transition from velocity 1 to some critical value where we now have what looks like a first-order phase transition. And the phase transition's at a much smaller value, and we see that the velocity decays, and it seems to follow a formula that it's 1 minus the density to the 1/2 power. So we're trying to figure out why that is. But I think what's really interesting is to think of this role of synchrony, and there were two models that really showed this prominently. Has everybody heard of the prisoner's dilemma? So the prisoner's dilemma is a beautiful game theory model about cooperating or defecting, and it's usually thought of as a small player model. And in 1992, Nowak and May looked at the prisoner's dilemma on a lattice. So they thought about the spatial prisoner's dilemma, where sites could now cooperate with neighboring sites, or they could not cooperate with neighboring sites. So they put it on a square lattice. And they found that it formed all these beautiful patterns. And they conjectured that this had something to do with ecology. So it had to do with the food web and ecosystems and how things get organized into domains so that animals have territories and interact with neighboring animals. So this appeared as a paper in Nature in 1992 because it really had these beautiful self-organized patterns. And then a year later, Huberman and Glantz actually did the same spatial prisoner's dilemma, but without synchrony, and it didn't do anything at all. So, so that was really one of the first papers to point out how synchrony can really lead to a lot of self-organization that we see. So we have to think about where that's a valid role. So there's several of these things that we have to think about when we're modeling, whether it's discrete time is valid, the dependence on aspect ratios. And then for traffic flow in particular, there were several implications that we could draw. And that is, everybody thought that things jammed at a density around 30%. And we showed that you could, based on the lattice conditions, actually achieve states that had very high throughput. So those intermediate states have an average velocity right around 2/3. So this was in a regime where everybody felt that there was no throughput at all, and the velocity should be 0. But we saw that based on your choices of L and L prime, you can actually get high throughput and flow in this regime. And also the onset of jamming can be delayed based on the geometry. So those were implications particular to traffic flow. And a lot of people have been looking at this BML model in many different contexts, so mostly in traffic, but lately people have started thinking about it as modeling information flow in organizations. So they want to think about the red cars moving on the horizontal as being information flowing between coworkers, and the blue cars as flow between red and blue interaction as information flowing up the hierarchy in an organization, and trying to think about when a system jams, so when the information in a social organization just totally jams. So this model has been highly influential, and it continues to shape people's thoughts. So it's really interesting to think that there is this regime that went undiscovered for a long time. So I just wrote a review paper that's appearing in the journal Complexity, and it's on this interplay of statistical physics, probability, and computer simulation, going through several of the models that sort of illuminated us on some of these things, the role of synchrony, the importance of the aspect ratio, and what they're used for, what these models are used for, like dynamical jamming transitions. So, these models are all, and actually this Bootstrap percolation model. This is a really interesting one because it's one of the only ones where rigorous proofs about its behavior exist. And this is actually the model I alluded to earlier, that the proof shows the percolation threshold to be very, very different from what the experiments do. And when it first came out, nobody really understood what was going on. But after a few years of working it out, we realized that you have to implement Bootstrap percolation on a lattice that's like 100 billion sites by 100 billion sites before you'd even get close to what the numerical results look like. And now Bootstrap percolation is used often as a model for jamming in random media. So now here's the good question. So if I'm thinking about random media in a physical situation, so I'm interested in looking at the gel, or I'm looking at some polyelectric material, and I want to understand its jamming properties, which one do I care about? What the computer simulation is going to tell me, or what the asymptotic mathematics is going to tell me? So we have to figure out which is really the relevant regime that applies to our problem. And I just want to close by I know I'm talking fast, but I want to close by talking about one final model, which is really beautiful. So this model, the other models that I've mentioned, Bootstrap percolation, BML, Prisoner's Dilemma, those all sort of came, the BML and the percolation really come from the world of statistical physics and have moved into probability because they're such beautiful models. But this is a great model because it was introduced in the world of probability, and I'm trying to find the connection to statistical physics and what it models in reality. And this is called the Rotor-router, and it's a model introduced by Jim Propp a couple years ago. And it's basically a deterministic walk on a lattice. So we're going to start with an empty 2D square lattice. And each site is going to be able to route particles. So it has a rotor, which is an arrow. And the arrow can point in any of the 4 lattice directions, north, south, east, or west. And it's going to be a really simple dynamic. So I introduce a particle at the origin, and it's going to follow the signs dictated by the rotors. And whenever it leaves its site, it rotates the rotor by 90 degrees. So the first particle, this is what the system would look like after 4 particles have come in. So the first particle comes in at the origin. It moves to the site to the north, and it rotates the router at the origin to the right. The next particle comes in, fills the site to the right, rotates the rotor south. The next particle comes in, moves south, rotates the rotor west, et cetera. So now it gets a little bit more interesting when you start adding more particles. So the 5th particle comes in, and it's going to move to the north, because that's the direction that the rotor's pointing, and it's going to leave this rotor pointing east. And then it moves into this site, and it's going to move to the north because that's the direction the rotor's pointing, but it's going to leave the site pointing to the right, and then move into the unoccupied site. So it's a deterministic walk on a lattice. And the routers have 4 states, north, south, east, or west, so we're going to color it according to the state of the router. So this is what the Rotor-router looks like after 200,000 particles have landed. So the colors correspond to whether the router is pointing north, south, east, or west. And there's a couple just amazing things about this model. First of all, it makes a perfect circle. So perfect circle in the fact that if you define things as like the in radius and the out radius, so the in radius being the shortest distance from the origin to any boundary, and the out radius being the longest distance from the origin to the boundary, they differ by 1 lattice site. So it's as close to a perfect circle as you can get on a lattice. And there's also so many other interesting things, like all the patterns that it's forming. So this is actually a abelian model. It's commutative. So I showed you introducing one router at a time, one particle at a time. But I can actually introduce all the particles at the same time, and they're going to end up in the same configuration, because I don't care about the identity of the particles. I care about the state that the rotors are left in. So since I don't care about the particle identities, I don't care which individual particle ended up in a site, but they're going to leave the rotors unchanged. And what's really fascinating is, I'm going to see if I can zoom in here a little bit. Oh, good. So if we start zooming in, you can see that there's all this fine structure. And what's really interesting is that as the multi-particle router is executing its dynamics, it realizes many configurations that we see in the abelian sand pile model. So these are 2 models that are completely unrelated to each other, yet show a lot of the same phenomena. And I just don't want to get into that since I'm out of time. So the Rotor-router is this beautiful model that just got introduced recently, and I think it illustrates well this interplay between the computer simulations and the probability theory, and now we're trying to find out the statistical physics behind it. And I'm just going to close with giving you some pointers to some further reading. So the BML model introduced in 1992 by Beham, Middleton, and Levine, the paper on the existence of these intermediate states that appeared in PhysRev-E in 2005. And then the Rotor-router was introduced by Jim Propp, but he never wrote it up anywhere. And there's a great mathematical intelligencer article by Kleebler on where he introduces the Rotor-router to the more general public and has great pictures. And then Lionel Levine and Yuval Perez just recently were able to prove some properties about the router being spherical. So they could prove some aspects of it. And then here's a pointer to the review paper highlighting these models and their interplay that's going to appear in Complexity in a couple weeks. Thank you.
There was the situation where you had 2 different phases that you could be, or 2 different flow rates that you could be in. Do you know anything about the proportion of those if you start with a random setup?
Repeat the question. So the question was about looking at how there are 2 different intermediate states that you could be in. So on these Fibonacci lattices, there's 2 intermediate states. And it was trying to understand if we could predict which state we'd end up in. Oh, what the proportions are, yeah. So there's so little that we understand about this model. I know that as you get to higher and higher density, the proportion of things in the lower state increases. So the high flow ones are for low density, the low flow ones are for high density. But what's really interesting is that this model isn't monotonic. So I can take one of these systems that jams, and I can add more particles and take it to a non-jamming system, because I can put them in just at the right precise microscopic place that they keep a jam from forming. So adding more particles doesn't, on average, makes a system more likely to jam, but it doesn't make an individual configuration more likely to jam. So I think that's one of the hard things of this model.
So in the model of Kenyon and Wilson, they show that the behavior very much depends on the aspect ratio, and it really depends on the number theory of the fraction L over L prime, right? Is there evidence for a similar behavior here?
So the question is looking at the model of Kenyon and Wilson, where they looked at the percolation on the honeycomb lattice. And they found, what did they find?
The behavior really depends on the primes that divide the fraction L over L prime.
Oh, okay.
It's a very specific way in which this works.
Okay, yeah. So they found that that there were a lot more deep number theory things in there. So it wasn't just having L and L prime be relatively prime to each other, but there were some more features, fine-grained features. And I think there probably are some here too. And what's interesting is if you simulate this on a L by L prime lattice, you get this beautiful periodic structure. If you simulate it, so you add one more lattice site. So instead of making it L by L prime, you make it L by L prime plus 1. You don't get these periodic structures. You get randomness on top of the structures. So I'm sure that there is a lot of stuff to study, but I don't know what to start with.
So you may have just answered my question, but you implied in your analysis that it was the golden ratio that was governing the Fibonacci, and not the precise Fibonacci.
Yeah.
But there are other fractions that approximate the golden ratio that are not Fibonacci, that were nearly as close. From what you just said, you'd expect that they would be chaotic, and it's the actual Fibonacci that matters.
Well, so what matters is that so the question was that there are other ratios of numbers that approximate the golden mean. So it's not just the Fibonacci sequence, which is exactly the golden mean, but there's other ratios that are very close to it. So what would we expect to happen if instead of having a
Fibonacci is rational, so it can't be exactly the golden mean.
Okay, fair enough. So the Fibonacci's approximate the golden mean.
Approximates about that much.
Yeah.
Is it chaotic?
No, so the Fibonacci's aren't chaotic, right? They're periodic, and anything that is close to, if they're relatively prime to each other, they end up basically forming these periodic structures. But yeah, I don't know. That's a good question. I got to think about that a little more.
Okay, if there are no more questions,
Thank you.
speak or any other questions?